This brief review concerns itself with the topics in the linked outline, starting with number 26, which has to do with the writing of rate of change or differential equations. A couple of examples. To say that the rate of temperature change is proportional to the temperature, how would we write this in the notation that we've developed to represent rates of change? Well, the rate of change of temperature is dt over dt, d big T for temperature, change in temperature, or d little t for change in time. And temperature, of course, is just T, if that's what we're using for temperature. And so we're going to say that d big T over d little t is proportional to T. Now, proportionality. Y is proportional to x means y equals kx. So that to say that this derivative or this rate of change is proportional to this is to say that d big T, d little t equals kt. That's how we're going to write that differential equation. There's no big trick to this. Sometimes there are tricks to solving these equations, although this one is very easy to solve, as we'll see shortly. Other possibilities, just different proportionalities. Listing of proportionalities. Y inversely proportional to x is written y equals k over x. Y proportional to x squared would be y equals kx squared. Y inversely proportional to x squared is y equals k over x squared. So another idea that we've seen, the rate of depth change. Okay, the rate of depth change is proportional to the square root of the depth, it turns out, when you have water flowing from a hole in the bottom of a uniform cylinder, or at y equals 0 in a uniform cylinder, wherever that happens to be. The rate of depth change is going to be dy dt, the rate at which y changes. The square root of depth is the square root of y, and the proportionality then is dy dt equals k square root of y. Still another example. The rate of population change is proportional to the product of the population and the difference between population and carrying capacity. This is actually a problem in the text. Well, the rate of population change is obviously going to be d big T over d little t, using big P for the population. If we use L for the carrying capacity, then the difference between population and carrying capacity is going to be P minus L. Population, of course, is P, so the product of population and this difference between population and L minus P translates into product of P and L minus P. So to say that d big P dt is proportional to the product of P and L minus P, we write like this. Here's a product of P and L minus P, and there's K. And that's all there is to that.